Section 8.4, Mathematical Induction. Objectives. I'll read them. Use mathematical induction to prove statements involving a positive integer n. Find the sums of powers of integers. The vocabulary key concepts. First one is the principle of math induction, and the second one is sums of powers and sums of powers of integers. I'm warning you, this principle is a little bit challenging. I expect questions on this idea. Let's move on to the next slide. So here's the principle of mathematical induction. This is what the book presents to you. I find it a little bit confusing, so what I decided to do is kind of break it down for you. So let's get rid of this. And this is what you want to be using, and this is what I'm going to be using in the video. So PMI, and I broke it down into 4 steps. Now, whoever came up with this is a remarkable principle, and is the work of a genius, and is basically you're carrying out an argument. And this argument, I broke it down for you as 4 steps. In the video, I'm not going to talk to you about the argument, and I'm not going to try to convince you about the argument, but I'll do this in class, okay? And you're going to see why I'm saying that this is the work of a genius. Let's move on to the next slide and apply this principle. So here's number 1. It says use mathematical induction to prove the formula for every positive integer n. So there's the formula. So first step, let's apply the first step in PMI. It's basically to show that it's true for the formula is true for n equals 1. And how do I get this? All I'm doing, let me get a pen here, is this, the first term is 3, and you plug n equals 1 into this expression here, and we end up with the following. I simplify the right hand side, and I know that 3 equals 3. So I just showed that it is true for n equals 1. Let's go to the second step. Second step is actually pretty easy. It may seem redundant, but we use the second step in step 3. It's very important for you to do step 2. So all we're going to do is we're going to assume that it is true for n equals k. So over here, wherever you see an n, we plug in a k. And that's all we do on step 2. Step 3 is basically to show that it is true for n equals k plus 1. This is where most of the work is going to take place. So when we let n equal k plus 1, this is the expression that you're going to be working with. Let me clarify this here. And again, if you want me to clarify this further, just ask me and I'll be more than happy to do this in class. How do I generate this expression? This is how I come up with this. Notice that from here to here is basically the left side of step 2. How do I come up with this other expression? Keep in mind that I'm trying to show that it's true for n equals k plus 1. K plus 1 is 1 more than k. So that's why I add 1 more after 8k minus 5. So what's the next one after 8k minus 5? 8, which is here, and then k plus 1, bring over the minus 5. So this is basically just the left side. How do I come up with the right side of this expression? Instead of writing k, I want to show that it's true for k plus 1. So wherever you see a k, I add a 1. K plus 1, k plus 1, and so forth. Okay? Like I said, I can clarify this a little bit more in class. So here we go. Now what I'm going to do is I'm going to try to show that this left side is equal to this right side. That's why you see a question mark here. And I know that all this is equal to this from step 2. Look at it. All this is equal to k times k for k minus 1. So what I'm going to do next is all this is going to become just k times 4k minus 1. at this point, all I did is I simplified this, and I ended up with 8k plus 3. I still have the question mark because I want to show that it is true. Then I distribute the 4 here, and I do a little bit of simplifying, and I end up with this expression. So now my goal is to show that this expression is equal to this other expression on the right hand side. I don't have enough room, so let's go to the next slide. Here we go. So this is what I want to do. I want to show that the left side is equal to the right side. So then I do a little bit of algebra. I'm just going to work on the left hand side. So once I distribute the k here, I get the following. And then at this point, I am going to combine these two middle terms. I get 7k. At this point, I have a quadratic. All I'm going to do is I'm going to factor this quadratic. Once I factor this quadratic, guess what? It's equal to the right hand side. So I just showed that it's true. Step 3 is completed. And I'm basically done with the hardest part of the problem. Step 3 is the hardest part of this problem. So now is step 4, which is basically to write a conclusion. And this is the conclusion that I need to write down. Therefore, by the principle of mathematical induction, the formula is true for every positive integer n. And like I said earlier, basically you're presenting an argument. And you should be able to follow this. If you still don't understand the nature of the argument, I'll clarify it in class. Let's move on to number 2. Here's number 2, same directions, different formula. Step 1. So we show that it's true for n equals 1. So the first term on the left hand side is, excuse me, let me get the pen, 1. And then we're going to plug in n equals 1 here. And we get the following. Is this true? Yes. Once you simplify it, the right hand side is equal to 1. Step 2. Assume that it's true for n equals k. So wherever we see a k, an n, we're going to substitute a k. And this is the expression that I get. And again, this is what I'm going to be using on step 3. So now, show that it is true for n equals k plus 1. This is where most of the work will take place. Again, how do I generate this expression? Well, up to here is coming from step 2. Since I want to show that it's true for k plus 1, I need to add one more. I need to add 1 to k. So here, that's why I have 3. And then instead of having just k, I have k plus 1 minus 2. On the other side, how do I generate this expression from here? Instead of using k, I need to use k plus 1. And that's why you see this. So at this point, I know that this part from step 2 is equal to the following that you see here. So this is what I'm going to be working with. I need to show that the left side is equal to the right hand side. That's why you see the question mark there. Not enough room. Next slide. So here we go. I am going to ignore the right hand side and I'm going to work with the left hand side. So I distribute this k over 2 into this binomial, and then I rewrite these two terms with the denominator of 2. This is all algebra. And then at this point, I combine these two because they have the same denominator and they're like terms, and I get 5k over 2. From here, I notice that I have a common factor of 1/2. So I pull it out, and I get this trinomial times 1/2. From here, I can factor this quadratic, and I get the following. And notice that the left side is equal to the right hand side. So I'm done with step 3. Step 4 is basically to write this conclusion, and this conclusion needs to be present. If you don't write this on your homework or on the quiz or test, it's not, excuse me, not the test, I take it back. You already took the quiz. On the test, if you don't write the conclusion, it will be considered wrong. Now I'm using these little 3 dots These three dots represent the word therefore. So it says, therefore, by the PMI, the formula is true for every positive integer n. Let's move on to the next problem. Same directions, different formula. Step 1, show that it's true for n equals 1. And now you should feel comfortable where I'm getting this from. And of course, 2 is equal to 2. Step 2 is to assume that it is true for n equals k, or just substitute k wherever n is, and I get the following expression. Step 3, this is where the work, most of the work will happen. So then I get the following expression, and by now you should have an idea how do I get this. And like I said earlier, I can clarify this in class. So now, what I'm going to do is I'm actually going to distribute this to the following way. I'm going to distribute this 2 to all the terms up to here, and then this 2 into the last one. And I get the following expression. Why? Because it makes it easier to work with. And then from step 2, I know that all this, what you see on the left-hand side here, is equal to 3k minus 1. So then this is what I'm going to be working with. This is what I want to show. I want to show that this left side is equal to the right-hand side. Not enough room, so I'm going to move to the next slide. So here we go. Ignore the right-hand side. I know that this is equal to 1 times 3k. And then instead of writing the parentheses, I express it this way. And look here. These two terms are actually like terms. And I can combine them. This is 1 3k and this is 2 3k's. So how many 3k's do I have in total? I have 3 3k's. And then bring over the minus 1. And then at this point, I just use my rules of exponents that I learned in Algebra 1. I saw them again in Algebra 2. And this expression that you see here is actually the same thing as what you see here. And at this point, you should notice that it's equal to the right-hand side. So I'm basically done with step 3, the hardest part. And then I cannot forget to write my conclusion. And once I do this, I'm done with the problem. Let's move on to the next slide. This is just basically the same type of problem, but it's just given to you differently. Now, notice that here we have sigma notation, but every single one of you should know how we can generate the following expression on the left-hand side, just by plugging I equals 1, I equals 2, I equals 3, and then dot, 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 plus the upper limit of n, and this is basically the same. The right-hand side is the same. And you're going to be working with this formula, and I'm not going to do this, but if you want me to, I can do it in class. And we just basically apply the same steps from problems 1, 2, and 3, and we are done with number 4. Let's move on to the last slide. It says find the sum using the formulas for the sums of powers of integers. Not to worry, I'll provide these on the test. So you have to compute this. Excuse me. You have to compute the summation notation of this expression, lower limit being 1, upper limit being 10. Now, you can actually do this by actually writing 1 to the 4th plus 2 to the 4th plus 3 to the 4th all the way to 10 to the 4th, but you're going to be here for a while. That's why I provided these formulas for you. Notice that this formula, since you're raising the n to the 4th power, that means that we need to apply this formula you see here. So I highlight the formula that I need to use on this problem. Now all you need to do, since the upper limit is 10, wherever you see an n, you're going to plug in 10. If the upper limit was 5, you plug in 5 for n, and so forth. So that's what I did here. And then at this point, all you need to do is you need to do a little bit of computation, simplify, and you end up with your answer. This is how you find the sum using the sums of powers of integers formulas. The last one is number 6 here. Before I compute this, what I'm going to do is I'm actually going to distribute the sigma notation into these expressions here. Sort of like the distributive property, and that's how I end up with this. So now, what I'm going to do is the following. Notice that this is the following formula, and this one is the following formula here. So once I apply the corresponding formulas, again the n is equal to 40. That's why you see 40 here, 40 here. I do a little bit of computations here. I get the following number for the first part minus the following number, 820. And then once I simplify this is my answer. And this basically concludes the video